welcome to another exciting adventure in the land of physics. We're going to talk about Newton's third law today. Now, this is what you're used to knowing. For every action, there is an equal and opposite reaction. Do me a favor and delete this from your brain. Okay, I personally hate that because when people think of reaction, they often think of time passing. And so they think, oh, okay, one thing happened and then another thing happened sometime later, or this hit, then that hit. There's always, I feel like time passes. Students often, they don't truly understand what's happening here. So what I really want you to understand is this definition. When two objects, these have to be different objects, interact, they create a single force. That can be seen from two different points of view. You really could say frames of reference, but I decided to keep the vocab a little more simple. So that means that when two objects interact, there's only one force. Okay, so it's not like an action-reaction. It means when two objects interact, they only create a singular force. So if I have two different objects colliding, now back in the days of yore, I used to play football. So I have football player A here. Look at that beautiful football player A. And they're going to smack into a much larger football player B. All right, a nice head-on collision. Now, after this collision, so this is like the before, and then after the collision, player A gets launched through the air, it's going flying, and that's a backwards B. Player B, I don't know what just happened there. Player B just keeps plowing on ahead. Okay, so you launch them. The question that you're traditionally asked is, which player applied a greater force to whom? And the answer is neither. They applied the exact same force. Because in the situation, let's count the number of objects. 1, 2. There are only two objects involved. So if you look, how many forces can be created? A single force. Only one force. What that means is that neither could have applied a greater force to the other because there was only one force applied. All right. Now the result of that force is independent of the force itself. Okay, there's external forces, which we'll talk about with other things, but the force itself is not what sent that person flying, and the other person just kept walking along. External forces were at play, that's why we'll talk about that in a second. But one object, two objects, you can only create one force. Now if you go back in the locker room, they're both going to have bruises because they both hit each other, and they're both going to say, man, he hit me, or she hit me and she hit me, whatever. Okay? They're going to say that they were hit. Each of them were hit because each of them will receive a bruise of some form or another. Okay? Because again, they are each interacting with each other. It's just seen from two different points of view. So when they hit right here, that collision, so let's go over here. So when A hit B, all right, so at this moment of impact right here, A and B hit each other. And the force on A by B is equal but opposite to the force on B by A. Okay? So we're just using a little notation here. So this is the force that A applied, or on A by B. This is the force on B by A. They are equal but opposite in direction because only one force, the force between objects A and B, was created, but it's seen from 2 points of view. They hit me, and that's why they're in opposite directions. Okay? So that's what that really means. So now let's break it down to some real life scenarios. These are the most common physics scenarios you'll probably run into. And this is the old-fashioned tug-of-war, so bear with me as I attempt to draw people in a tug-of-war contest. So let's see, we'll have person A, person B. All right, they're in a tug-of-war. That's not too bad. I understand what's going on. All right, so here's person A and here's person B. So now they're in this tug of war. Let's say person B seems to be winning. All right, so we're moving in this direction. Question again, who is applying greater force to whom? All right, think about it for a second. They're equal. I hate to break it to you, they're equal. First of all, a rope can only have one force in it, so a rope just transmits a force. So they might as well just be holding hands and just pulling against each other. And so A is directly interacting with B, B is directly interacting with A. We only have two objects interacting, so again, we only have one force. Now the reason why B is winning is because if I draw a force diagram for each of these objects, so here's A, all right, so we'll draw a force diagram for A, we'll draw a force diagram for B over here. So A's got the force of gravity pulling them down. The Earth is pushing them up with a normal force. They have a force of tension on A by B. And then there's the force of friction on A by ground. All right. Over here, if we look at B, I should probably color code these. Let's try a different color here for B. Let's do some blue. So if we look at B, B has a force of tension on B by A. It's being pulled that way. B has friction, force of friction on B by ground, pushing it that way. And then it also has the Earth holding it up, and the Earth's also pushing it down at the same time. Love-hate relationship. And then these are balanced. I should probably go back and put my tick marks. I'm going to put doubles on these because different size people. But if we look, B and A and B, two objects. So these forces are actually the exact same force seen from two different points of view. So these are the exact same force value. The reason why B is winning is because this force of friction is greater than this force of friction. So they're pushing on the ground harder than A is pushing on the ground. That frictional force is greater over here, and that's why they are starting to win the fight, because they're moving to the right here. If we were moving to the left, all this stuff would be identical. The only difference is this force of friction would be greater than this force of friction. So if you ever win a tug of war, it's not necessarily who's the strongest, got the biggest arms, things like that. You want to see who's got the biggest legs so they can push, and who's got the best shoes so you've got some traction. Because if you don't have the right footwear, you're just going to go sliding on the floor. Been there, done that. Okay? But again, if we use our on-by notation, you can see that there's only two objects involved, so those two objects are only creating one force. So again, two objects give you only one force. And this is the core of Newton's third law. All right? So hopefully that helped. A little on-by notation is always good. And if you got any questions, please let me know. But good luck with the assessments.